Hi, I'm Dan Bauer.
I'm Emma Crone.
And I'm Patrick Murphy, and for our 201 final project, we built an induction furnace.
The intent behind the induction furnace is to be able to heat up conductive or permanently magnetic materials. Our style of induction furnace is comprised of three different subsystems: the power switching, the tank resonator, and the power supply and high frequency limiter. The power switching subsystem controls the flow from the power supply to the tank resonator circuit by alternating the path to ground. This is done by activating and deactivating two power MOSFET switches. The activation of the MOSFET requires a potential across the transistor's gate. This creates a conduction path between its drain and source. The MOSFET gate has an internal capacitance. The point of these resistive loads is to form an RC circuit with a MOSFET to control the time it takes to charge or discharge the gate. This is the time it takes for the switch to turn on and off. Schottky diodes are placed between the gate and drain of the opposite MOSFETs to make use of their fast switching capabilities to discharge the gates of the MOSFETs. Excessive heating occurs on the MOSFETs due to the internal resistance along the conducting path and power losses while the device switches between its on and off states. Because of this, appropriate heat sinks are required to evacuate heat.
The second subsystem, the tank resonator subsystem, which can be seen here circled by the red, is made up of the inductor coil and the capacitors. They are connected in parallel. The inductor coil is center tapped at that point it connects to the choke inductor, which is here. The circuit is a self-resonant system. This means that it will run at the resonant frequency of the attached coil and capacitor. The resonator is technically an LC circuit. This means that charge is built up in the capacitor then discharged, which induces a current into the inductor. The inductor then stores the energy. The LC circuit oscillates. The devices charge and discharge each other. The frequency created by the AC waveform is the resonant frequency. This means that the total impedance should be zero. When a conductive or magnetic object is placed inside the inductor coil, an inductive link is formed. This causes an energy transfer from the tank resonator subsystem to the object.
The third subsystem is a frequency limiter circuit. It's comprised of a power supply and the choke inductor. The choke inductor blocks the high frequency signals from the power supply and limits the current into the system. The power supply drives the resonator subsystem, which transfers the power to the object being heated. The more current provided, the faster the object will heat up.
When the object that is being heated is inserted inside the heating coil of the resonant tank circuit, an inductive link is formed. The energy in the magnetic field induced by the rapidly changing currents passing through the coil induces very large currents in the object. This is because a solid object can be seen as a single-turn inductor, and the turns ratio of two coils is inversely proportional to the currents through each. These currents are specifically known as eddy currents, and when passed through the conductor, produce heat in what is known as joule heating. The resonant frequency of the system is also a factor in the heating of objects. The faster that the current alternates, the closer the current density in a material pushes towards the surface and away from the center. This is called the skin effect. In doing so, the effective resistance of the material increases and causes more joule heating in the object. In magnetized materials, a form of heating occurs in what is known as hysteresis. In this image, the arrows show how the magnetic field strength H and the magnetic flux density B vary as a current alternates through two cycles. Because dipoles are becoming magnetized in different directions, depending on the current passing through them, they generate frictional heat. Because these dipoles like to hold their position past the time that the current alternates through half a cycle, this residual magnetization causes a different starting point on the graph once a full cycle is finished. The area inside the BH curve is directly proportional to the amount of energy lost in the form of heat within the magnetic core.
To find the value of the resonant frequency which the tank resonator subsystem resonates at, we use this equation where L is going to be the value of your inductance and C is going to be the value of your capacitance.
We use this equation to compute the inductor and choke inductor values. Here we have mu sub 0, which is the relative permeability of free space, mu sub r, which is the relative permeability of the material inside the inductor, A, which is the area or the cross-section of the coil, n squared, where n is the number of turns in the coil, and L, which is the length of the inductor.
Go for it.
In our first attempt at creating the circuit, our estimation of the inductance in our resonant tank circuit was much lower than our actual value. This caused the circuit to resonate at a much lower frequency than originally guessed. The power delivery of a single power supply wasn't enough to get the object up to a sufficient temperature. In order to up the resonant frequency, we removed several parallel capacitors from our resonant subsystem.
As can be seen in these pictures, this is the original signal we had with 10 capacitors in parallel and a single power supply producing 100 watts of energy. This second image, we have the visual of the same signal with only 5 capacitors and 2 power supplies in parallel, producing roughly 200 watts of energy. Channel 1 and Channel 2 are measurements across each side of the center tapped inductor, and the mathematical channel is their difference. After hooking up 2 power supplies in parallel and removing half the capacitors, the peak temperature we measured across a piece of heated steel was 500 degrees Fahrenheit. At that point, the highest resonant frequency was about 200 kilohertz.
Goodbye. Thank you for watching our project on our induction furnace.